Hello there, Mr. Chan here for Algebra 2. We're going to start lesson 4-3, multiplying and dividing rational expressions. Please grab your note takers, the student companion, and turn to page 99, and let's get started. At the top, though, I'd like to talk about some skills that they're expecting you to have from Algebra 1, and they are factoring. When it comes to factoring polynomials, there are some things that you should look out for. So write this down. Factor polynomials. Factor means, of course, to break things down into pieces. It's a form of division. We're going to break it up into little parts. Polynomials, of course, are algebraic terms that include monomials, binomials, trinomials, etc. They're basically a family of terms. Just a family. Or a sum of terms. When it comes to factoring or dividing, you want to try factoring out a monomial Gcf, or greatest common factor. You want to check to see if you have any difference of squares. You want to look for any sum and difference of cubes. That we learned last semester. And other things including factor by grouping. 4 more terms. The challenge for you guys in this section is remembering a lot of these techniques. If you get stuck, please let me know. Understand that we will be looking at multiplying and dividing rational expressions in this section. Now, before we do that, we're going to jump into this opener involving a very innocent looking equation, y equals x plus 2, as you see right there in front of you. Of course, this is a linear function with a slope of 1 and a y-intercept of course, 2. And as you can see off to the left there, we have our y-intercept 2. Its slope is 1 over 1. Question. What is the domain of this function? Domain, of course, are the x values. And no matter what you pick for your x value, it will always work. Plug in 0, plug in 1, whatever. Every x value works. So in this case, no matter what you pick, it's all real numbers. Can be plugged into there. So the domain is all real numbers. That fancy little symbol. All right. Now, before we move on to question B, I want to remind you what we learned about last section. We graphed a new shape called hyperbolas. Hyperbolas have branches that are guided by asymptotes. We have horizontal as well as vertical asymptotes. And just to keep track of this, we talked about how asymptotes, vertical ones, are not part of the domain. So kind of put that in the back of your mind. They're not part of the domain. And the reason why I bring this up is because this opener involving a linear function, 1x plus 2, doesn't have any asymptotes. All the domain values are possible. But moving on to the second question, we're going to ask you guys something very strange. Can we sketch a function that resembles the graph up there that we just had, a line, but restrict its domain to exclude 2? So this is kind of strange. Let's go and draw our axes. They want us to exclude 2. And I think we're going to go by 2s, by the way, to kind of scale it relative to what we have in the first graph here. I'm going to copy the graph that we have up there, y equals x plus 2, but I'm going to exclude, kind of like having a force field, through x equals 2. So here, at x equals 2, it does not exist. It's not part of the domain. So I'm still going to draw that line, y equals x plus 2, but I just can't draw the part where x equals 2, and when you plug in 2, it becomes 4. So when I connect all these, what will happen in algebra is when you exclude that part of the domain, it actually, there's a gap we call a hole. Isn't that weird? So this restriction is literally telling you x cannot equal to 2. When it cannot equal to 2, it's saying that that does not exist. This is called a hole in the graph. Isn't that strange? Now, how do we create a hole algebraically? That leads us to our next part of this opener, okay? Let's go on down to letter C. Consider the function you have just sketched. Yeah, it's a line with a hole. What kind of a function might have a graph like this? Now, they don't expect you to kind of figure that out algebraically. I'm going to walk you through this. Let's consider the equation right now. X plus 2. Now, you notice I've drawn a fraction bar here. When we have exclusions or holes, we are incorporating a vertical asymptote. Pretend at x equals 2, there is a vertical asymptote. Vertical asymptotes are found by looking at the denominator, as you recall from the last section. In the denominator, x minus 2 represents the vertical asymptote that would be there if you were to graph it. Now, I just pulled an x minus 2 out of the air. I have to make it disappear again. So algebraically, I just introduced like a invisible 1 right there. That's the trick. X minus 2, by the way, in the denominator, as you recall from the last section, is where you find vertical asymptotes. You set the denominator to 0, and you solve it by adding 2 to both sides. And there it is. I'm kind of working backwards here. This is the actual equation. That is the vertical asymptote, and that's why I introduced it in the first place. Okay, this is the vertical asymptote. But I don't want it there because it graphs a line, not a hyperbola. This is kind of strange, isn't it? So think about it. I'm actually creating a rational expression, P of x over Q of x. I've introduced a hole out of the air. So what are we trying to say? This function, x plus 2, can be rewritten if you were to simplify the numerator as, and in fact it's a product of conjugates there, x plus 2 times x minus 2. When you FOIL it, you'll get x squared minus 4 all over x minus 2. It is a rational expression, but it graphs a line with a hole in it. Isn't that strange? So what is a hole in this case? A hole is a vertical asymptote that cancels. Whose factor cancels? And that's the key, ladies and gentlemen. See how they cancel? When you cancel a vertical asymptote with the numerator, it becomes a hole in the graph. You have to consider that. Isn't that crazy? Let me show you that with Desmos. Oh, there are my equations right there. Great. You might need to move into the video a little bit. It's kind of hard to see. I have x plus 2 right there. We'll turn it off. I'm introducing the x minus 2, and it's kind of hard to, you can't see it here technically, but if I zoom in and I hover over 2, 4 and click on it, notice what the computer program tells you. It's 2 comma, it's not 4, it's undefined at that point. That is considered a hole right there, okay? In fact, I'm going to turn that off and show you that it is the same as this guy, x squared minus 4 over x minus 2. And if I again hover over there and whoop, it's a little off, there it is, 2, whoops, it's a little off, 2 comma undefined as well, okay? All right, let's go back and do the bottom of that opener there. So this is a strange idea, isn't it? Introducing holes in our graphs. It's kind of interesting. All right, next one. Does the graph of y equals 2x plus 6 over x plus 3 have a vertical asymptote at x equals negative 3? So this is kind of interesting. Your factoring skills are important. So I'm going to rewrite this problem. And I need to use all my skills from algebra. And please try not to reduce things. You can't reduce those x's. That's illegal. That's why I quickly put parentheses around them to force you to not reduce things illegally. 2x plus 6 is a binomial that can be broken down further. I'm going to take out a Monomial Gcf on top. I can take out a 2. When I factor out a 2, in the numerator, I'll be left with an x plus 3. Ah, interesting. Technically, x plus 3, the whole polynomial will cancel with the x plus 3 in the denominator. That is a hole. If it didn't cancel, that x plus 3 would be just a vertical asymptote, but because it cancels, it is no longer a vertical asymptote. It is now a hole. And that's not a vertical asymptote. So the answer is no, not a vertical asymptote. It's a hole at x equals negative 3. So this is a tie-in with the last section, which was lengthy itself. Now for the rest of the lesson, we are going to concentrate on practicing factoring, looking at holes, vertical asymptotes, horizontal asymptotes, I think they might ask, I can't remember. But we're going to be pulling in a lot of factoring. If you need to take a break anytime, please do so. Pause the video, whatever, okay? Let's move on to the next page and try example 1. Here we go. All right, here we go. This is quite the monster here. Write an expression equivalent to, holy cow, 3x to the 5th minus 18x to the 4th minus 21 over x to the 3rd, all over 2x to the 6th. Oh yeah, this is quite a handful there. Now before I move on, I just realized I want to show you quickly that last little problem on Desmos involving that particular problem. And they asked us about what would happen at x equals negative 3 right there. If I move my mouse up to here at the spot and hold on to it, and hold on, am I going to get it? I might have to zoom in a little bit at -3. Sometimes, oh, there it is. Did you see it? Yep, there it is. Oh, very difficult. Oh, there it is, undefined. You get the idea, you see it, right? There it is, okay? All right, back to our notes. So again, please be careful with your polynomials. You might be very, very, very tempted to cancel parts of polynomials. That's technically illegal. You want to parenthesize those polynomials and you zoom in a little better, a little more. And first thing you want to check, can we factor out a monomial GCF? That's what we need to look for. That is the key here. Look in the numerator. We have a 3 leading coefficient, 18 and 21. 3 divides into those numbers. Yay. So I can, part of my GCF strategy is to take out a 3. Any variables? Let's look at the 3 terms here. X to the 5th, X to the 4th, X to the 3rd. Yep. I can squeeze out or divide out an X to the 3rd. Okay. So that's your greatest common factor in the numerator. And when I factor out a 3x to the 3rd, I'll be left with, and I'm basically dividing, right? 3 divided by 3 is 1. X to the 5th divided by x to the 3rd is x squared. If your factoring skills are shaky, it's a good time to practice or ask questions, because this is something that was expected of you to learn from Algebra 1 and geometry. Next term, negative 18 divided by 3 is minus 6. And we have x to the 4th divided by x to the 3rd, that's x to the 1st, great. And then finally, minus 21 x to the 3rd divided by 3x to the 3rd, we have minus 7. Okay, that takes care of the numerator. Let's go ahead and see what we can do with the denominator. Let's look for the GCF in the denominator. Oh, we have a binomial. I can take out a 2, definitely. And I can take out x to the 4th. When I do that, I'll be left with, let's see, 2 divided by 2 is 1. X to the 6th divided by x to the 4th, you subtract the powers, that's x squared. And then 98, half of that is 49. X, oh, no more x's. Sweet, great, awesome. All right. Can I break down my polynomials any further? The answer is yes. Those can be broken down further, right here and right there. They can go further, can't they? Let's do that. I know. You didn't think factoring is going to come back to haunt you? The answer is yes. It will come back and haunt you year after year. Now, I recognize the top being a quadratic, that's factorable. That's an easy one. And the bottom one is a difference of perfect squares. How nice is that? Woo! That's an easy one, right? X squared is a perfect square. There's a minus sign. It's a binomial. 49 is a perfect square number. And that's definitely x minus 7, x plus 7. And in the top, we have, there's only one way to get 7. That's 7 and 1. And you do want a negative 6, which means I need a negative 7 right there and a positive 1 right there. So right now, we've broken down this rational expression into its factors, and we are asking for the domain, and we might as well find all the other stuff too, okay? Now look at the denominator here. Think about this. In the denominator, that's the key here, we have asymptotes and we have wholes as possibilities. In fact, we have 3 factors going on here. 1, 2, and 3. We have 2x to the 4th, set that equal to 0, because we're now looking for vertical asymptotes and wholes. They're basically the same. You look in the denominator, okay? So we have something times something times something. So we have 2x to the 4th equals 0. Divide through by 2, x to the 4th equals 0. And 4th root both sides, x equals 0 is one of our answers. Yay. Look at the second one, x minus 7. Set that equal to 0, solve it. Add 7 to both sides. And we get x equals 7. Nice. That's another possible vertical asymptote or whole. And the last one, in our denominator, we have x plus 7 equals 0. Subtract 7 to both sides. and we get x equals -7. Now here's the interesting thing. If any of these numbers, these factors cancel with the numerator, it automatically becomes a whole, right? We have 3 answers so far for vertical asymptotes and wholes, right? I know I don't have to do this much for you, but I wanted to point it out, okay? Technically, here's the answer, by the way. The domain is all real numbers except those 3 numbers. X cannot equal to 0, and X cannot equal to plus or minus 7. This is the real answer, by the way. We are technically done, but I want to point out, because when it comes to like making a connection to the previous section 4-2, hey, what constitutes a vertical asymptote and what constitutes a whole? So I just want to kind of distinguish them for you. Look at x equals 0. X equals 0, if you think about this, let me show you. X to the third cancels with x to the third of one of those. So this is going to be a whole because those cancel, ladies and gentlemen. That's a whole. Isn't that interesting? How about x equals 7? Well, look here. X minus 7 cancels. So this is also a whole if you were to look at the graph itself. And then finally, x equals -7 doesn't cancel. This is a vertical asymptote. So I just want to make that connection. I answered more than I needed to, but I wanted to make that connection, okay? All right, let's try another one. Ooh, if you need to take a break, please do so. More factoring on the way. Let's try example 2a next. Here we go. Okay, simplify each. Oh, did I ever simplify this for you anyway? I didn't. Whoops, my bad. So those cancel, and I'm actually left with my final answer here. 3 times x plus 1 on top, all over 2x times x plus 7 in the denominator. Sometimes people simplify this whole thing, get 3x plus 3 over 2x squared plus 14x. So if you were to ask to simplify them, oh, I did. Duh. Right, an equivalent to that. I guess they wanted us to simplify. There they are. Here's this one. Or that one. All right, there it is. Good thing I double checked. A little embarrassing there, make a little mistake. We're going to do the same thing with 2a and 2b. We need to simplify by factoring. We need to talk about the domain and deal with that. Here we go. Let me zoom in a little bit for 2a. And again, do not randomly reduce things that are part of the polynomial, parenthesize them so you are not tempted to break them apart individually. These are, oh, the top one is a quadratic that can be factored. In fact, let's see, 1 times 1, yep, 1 plus 1, that works. There it is. It's actually a perfect square trinomial on top. Interesting. That's a PST. Psst. On top. On the bottom, interesting, I can take out an x first. That's my Monomial Gcf. And that will leave me with an x squared minus 2x minus 3. And that is a quadratic that can be factored in the denominator too. So that, I took out an x. And that right there, that quadratic is easy to do in my head. X and 3 and 1. Let's see, one of them has to be negative. That's going to be the 3 to make a -2 in the middle. Again, if you are struggling with what I'm doing right now, you need to go back and practice. And this is something that we're assuming that you know how to do, okay? All right, in the denominator, we have 3 factors, x equals 0, x minus 3 equals 0, and x plus 1 equals 0. These are my vertical asymptotes, or wholes if anything cancels. And let's see if anything does cancel. Oh yeah, there's only one thing that does cancel, and that on the end is a whole when you solve it. X equals -1 is a whole. X equals 3 is not a whole. It's a vertical asymptote. And x equals 0 is a vertical asymptote as well. So these are all, let me write this down. We got a vertical asymptote, and this last one is a whole. Okay, very nice. We do have to mention the domain. The domain is all real numbers except x cannot equal to 0, 3, -1. Doesn't matter if they're wholes or vertical asymptotes. And the simplified version answer to this problem, of course, is what's been reduced. X plus 1 over x times x minus 3, or depending on which book, x plus 1 over x squared minus 3x, if you were to simplify that. Okay? Both of those are correct. Let that absorb into your brain a little bit. Let's take a look at letter B here. Uh-oh. Now, I already see this as something that a lot of you have not seen in a long time. Factor by grouping. There are 4 terms on top. One of the suggestions that we have kids do is factor by grouping. Back when I was a kid, we would line them up and split them in half and then factor a GCF from each half, blah, blah, blah. The technique nowadays that a lot of kids like to do is throw it in a box and see if we can factor it that way. So right now we're concentrating on the numerator, okay, folks? X to the third plus 4x squared minus x minus 4 is a possible factor by grouping polynomial, okay? So let's put the terms in there. X to the third, 4x squared, and usually 99% of the time they give us problems that do work. The key to factor by grouping is to find the greatest common factor in each row and column. First row, hey, I can take out an x squared, nice. Second row, starts with a negative. I do have to take out a -1. Nothing else happens to come out. First column, take out an x. And last column, take out a 4. It does work nicely, ladies and gentlemen. So my first term up there, in the numerator, I have x squared minus 1 times x plus 4. In the denominator, that is a quadratic that can be factored as well. X squared, there's only one way to get that. And 4, well, we have 2 pair possibilities, 1 times 4 and 2 times 2. The only one that works is 1 times 4. And interesting, one of them is negative, one of them is positive. There it is. And unfortunately, notice something interesting. Sometimes when you open a box of chocolates, you never know what you're going to find. And one of the factors from the factor by grouping situation produce a difference of squares. And that can be broken down further. Crazy. Wow. So that one can be broken down further as well. That one is x minus 1 times x plus 1. And let me bring everything else along for the ride. Wow. These can be uncovered and surprises will get to you. Let's go ahead and talk about the domain. The domain are all real numbers except the denominator right there. So split them up and solve. Before you cancel, okay? Don't cancel yet. These are pertinent to the actual graph itself because you want to look at the original problem when deciding what your domain is. Here, after you add 1 to both sides or -4 to both sides, you'll get 2 answers here. X equals 1, X equals -4. Those are your vertical asymptotes, I think. Unless things cancel, let's take a look here. X minus 1 cancels. So this is a whole. And oh my gosh, that's a whole as well. Both of them are wholes. They are not part of the domain. X cannot equal to 1 or -4. Interesting. The only thing left, this is crazy, is x plus 1. An innocent line when you graph it with 2 holes. All right. Any questions? Next, habits of mine actually is perfect timing. Bailey simplified the rational expression blah, 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 blah by dividing out the x squared terms. So she did this. and then dividing out the factor of x plus 2 to get 2. Oh, that's not good. Like that. And her answer was just a simple 2. Is she correct? No. This is illegal. You cannot cancel parts of polynomials. Only factors. Factors are separated by multiplication and division, okay? You can't separate pluses and minuses, okay? So this is a great lesson to learn. All right, example 3. So the next few examples is just more of the same stuff. I just want to point that out. Just because they call it multiplying and dividing doesn't mean we're introducing anything new. We're just doing more stuff. It's not a big deal, to be honest with you. If you're following along what we've been doing with example 1 and 2, the rest is just doing more algebra, just making you think that there's a lot to do. But you know what? First thing you want to do is you want to parenthesize everything. Yeah, parenthesize, go, 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 parenthesize. And sometimes there are some tricks to factoring, which are unusual, especially with number 3a. I already see it coming. I have 4 polynomials, of which a lot of it can be manipulated. X squared minus 16 definitely is a difference of squares right there. X squared plus x minus 90 is a standard quadratic. That 9 minus x is kind of weird, isn't it? That's going to come into play here in a minute in the denominator. But by the way, we are multiplying. Basically, we're throwing 2 rational expressions together. It's not a big deal. It's just a bunch of factors. And let's go ahead and break this down. So x squared minus 16 will be broken down because of the difference of squares. X squared plus x minus 90 is also break downable. 9 minus x, we'll take care of that in a minute. And the 4th polynomial can be broken down as well. So x squared minus 16 is definitely a difference of squares. And that will give me x 4 minus plus. That was easy. The second one, x squared plus 9 minus 90. Let's go ahead and break that down. I'll use a different color to kind of separate things a little bit. X times x and 90, let's see. I mean, we can go through all the possibilities, but one of them when added together will give me a 1x, right? So 1 times 90, 2 times 45, etc., 3 times 30. It's just not close enough. So somehow we need 2 factors that are close together by 1. How about 9 and 10? That works, see? Sometimes using your mental math abilities, it can kind of walk you to that. And one of them has to be positive. I need a bigger positive number, and the other one's negative. There it is. Oh, snap. You guys see this strange dilemma right there? Can those be canceled? I don't know. All right, let's get to the bottom. Use a third color, XX, 40. Ooh, 1 times 40, 2 times 20, 4 times 10 work, yay. Oh, wow, look there, all those factors. Look at all those factors, okay? They don't need any, well, they don't ask for, oh, they do ask for it. Okay, they do. They do ask for the domain, just like example 2. Fine. Now, 9 minus x and x minus 9 is a trick. Think of it this way. Pick a couple of numbers subtracting each other, just off to the side. Just make something up here. Like say 2 minus 7 versus 7 minus 2. 2 minus 7 is -5, and 7 minus 2 is 5. When you reduce that, you'll get -1. Guys, see that? Pick another pair, 3 minus 4 versus 4 minus 3, right? So this is kind of a trick you see on SAT and ACT questions. They love this trick. The trick of -1, folks. It's a trick question. 9 minus x, I want you to factor out a -1. Isn't that strange and kind of spiffy? That'll give me -9 plus x. -9 plus x is the same as x minus 9. That will cancel. that will be a whole. And before it becomes a whole, when I solve it, I'll get x, let's see, 9 minus x equals 0, negative x equals negative 9, x equals positive 9. That's not part of the domain, isn't it? So the domain x cannot equal to 9. That's one of my answers. And I'll work on the other two right now. That's a trick, okay? Remember that for your SAT. And ACT, they love negative ones when it comes to subtracting two numbers. Okay, it's a trick. Second one is negative 4. Great. That's not part of the domain. And the last one, x cannot, well, look at the negative 10. That's not part of the domain. Yay. And when we simplify the heck out of this whole thing, what do we get here? See, that cancels. Those cancel. Holy cow, what? Remember, this was part of the canceling right there, okay? So my final result with this is x minus 4 on top over negative 1 in the denominator. I will take, if you were to apply that negative 1 to the top, you would get negative x plus 4. In fact, I expect it to be even trickier. They might even give you this third possibility, 4 minus x, evil people, right? So there are 3 possible answers there. All right. So you can tell right now we're just practicing a lot of factoring, identifying what the domain is, and giving the simplified answer. Moving on to 3b. I'm going to parenthesize all those polynomials so I don't feel tempted to reduce anything. I do have a couple of monomials. That's okay. See that 4x? That's just 4 times x. And see that x squared up there? Just pretend that's x times x. And this one, just pretend it's 2 times 2 times x. Just pretend they're their own individual kind of thing. Now, I can see right away that I'm just going to basically break it all down so you guys can see it. X plus 3 is already broken down. 3x minus 18, I can take out a mono GCF. Definitely. I can take out a 3. When I take out a 3, I'll be left with an x minus 6. And then x squared, I'm going to actually break it down to xx. So you can kind of see it visually. 4x in the denominator is 2 times 2 times x. And we have a 6x plus 18. That can be also, that's also a mono GCF as well. And then the last one as well. Okay. And I can take out a 6 there. And that leaves me with an x plus 3. And the last one, I can take out a 4. That leaves me with an x plus 3. Now, I remember doing this a couple of years ago and thinking, it's going to be really exciting. I'm going to be canceling a lot of things. There's not a lot to cancel here. But I can tell part of the domain is all real numbers except x cannot equal to, look at these factors now. Here's 1 right there, 0. And this one is negative 3. And this one is also negative 3. Interesting. So I don't have to repeat that. So ladies and gentlemen, this is the domain. You'll have, let's see, at x equals 0, that's a whole. Because that cancels with one of those x's up there. X plus 3 will cancel with one of the x plus 3's up there. That's a whole. So both of them are wholes. Okay? So my reduced answer, anything cancel out? Let's see. Oh, look at the 3 and the 6. That reduces. 3 goes into 6 twice. Anything else go away? No, unfortunately. And I'll be left with a x times x minus 6 in the numerator over, I got to collect all those numbers, 2 times 2 times 2 times 4. That'll give me 32 over x plus 3. And that's the answer. And they might give you an alternative answer by simplifying it. You might get this as an answer when they simplify it, okay? Not as pretty as the one above. All right. This is turning out to be a long section, isn't it? Thank you for hanging in there. This is probably a 2-day lesson. Definitely. Let's move on to the next page. All right. More multiplying. Ooh, no big deal, right? They're trying to scare us. We're just doing more algebra. That's all we're doing. Just more algebra. Moving on to 4a here. Parenthesize your polynomials. We're multiplying by a Ooh, I don't know why they even have a separate problem. Just put it over 1 there. And let's just factor out monomial GCFs like it's no tomorrow. There's not a lot of room here left. I actually used some room down here. So we'll do that, okay? So here we go, 4a. I can factor out an x for the monomial. That leaves with an x squared minus 4 right there at the top there. And the denominator, ooh, that one is not easy to do. You can guess and check, or you can use a box method. I'm going to go ahead and do the box in the denominator here. But before I do that, I'm going to break up the 2x cubed problem. Let's do that. Take out an x. That gives me 2x squared minus 3x minus 5. I'll have to deal with that in a moment. So let's not worry about it right now, okay? So first off, I'm going to take the 6x squared and use the box method. You can use a diamond or AC hybrid, I don't care. First term, first box, last term, last box, middle term, lower left-hand corner. This is what I teach my students. Multiply the diagonal, a times c, I get negative 30x squared. Think of all the possibilities of getting negative 30x squared when added together. We're going to be negative 13. You know, I'll make them for you. Negative 130, negative 215, negative 3, 10. Which one of those will give me negative 13? Now, the middle one I just did, it's almost there. I just need a negative. So that means my combination should be positive 2, negative 15. And I'll put that in the box. 2x and negative 15x. That works, yay. GCF rows and columns. First row, I can take out a 2x. Last row, I'm going to take out a negative 5. First column, I can take out a 3. Yeah, all these things you're supposed to learn in Algebra 1 are coming back to haunt us, aren't they? And last column there, I can take out I can't take anything out except 1. Yay. So there it is. 2x minus 5. And of course, 3x plus 1. Running out of room, I need to squeeze it on down here. And oh, look, I have a difference of squares up here. Oh my gosh. A lot of crazy factors. Difference of squares. And this is a quadratic. Yeah, this is a lot. Here we go, set that up, all over, and we just got 2x minus 5 times 3x plus 1. So x squared minus 4, let's break it down of course. That is x minus 2 times x plus 2, great. And you keep your fingers crossed. Well, a lot of things cancel. This is what I'm hoping for. And over here, 2x squared, I'm going to guess that one. That's 2x. And x and negative 5, it's going to be right here, plus 1. You can use a box. I just did that on my head. Quick check. 2 times 1 is 2. Negative 5 times 1 is negative 5. 2 minus 5 is negative 3. It matches. I just did that on my head. Got lucky. Very good. Now take a look at this. We need to find the domain. The domain is in the denominator, and in this case, the domain is x cannot equal to, let's take a look here, 2 minus 5 equals 0, x equals to 5 halves, great. Over here, 3x plus 1 equals 0, x equals negative 1/3. So those are my domain values, okay? And unfortunately, the only thing I see canceling is the 2x minus 5. That is sad. The simplified form is all of that. Ouch. It's the rest of this. I'm so angry at this problem that I'm not even going to write it again. Okay. I'm not even going to simplify. That would be way too much work. All right, let's take a look at 4b. A lot of factoring. A lot of factoring. Here we go. 3x squared plus 6x. Let's try the Monomial Gcf. X squared minus 49 is the difference of squares. X squared plus 9x plus 14 is a standard quadratic that we can factor. Great. In the Monomial Gcf, I can take out a 3x. That leaves with an x plus 2. X squared plus 9x plus 14. Let's break it downable. Let's see, 7, 2, 14. Oh, 7, 2 work. Yay. Takes practice, doesn't it? And the difference of squares is x minus 7, x plus 7. Oh, x plus 7's cancel. That's a whole. That's also not part of the domain. The domain is, take a look at there, x cannot equal to 7 or negative 7. That's from here and here, right? That's in the denominator, right? Those are vertical asymptote and a whole. This is a vertical asymptote, and that was a whole because it canceled. And that's it. The rest of the answer is your answer, okay? I mean, I wish it would cancel more, but that is your answer. We just cancel the x plus 7, and that's it. So, nothing really too new on example 3 and example 2. Example 5. Oh, I meant to say 4 and 3. Sorry about that. Example 5 is this division. It's the same process with one extra thing. Recall from your algebra days, your elementary days, when it comes to dividing fractions. The key is to multiply by the reciprocal. That's the key. I learned this when I was growing up when it came to dividing fractions. Skip, flip, and multiply. Skip the first fraction. Flip, meaning exchange the numerator and the denominator of the second fraction. Some kids learned this third one, KFC, like the chicken. Keep the first term, flip the second fraction, and change the sign from division to multiplication. I mean, quick example might be here. Oh, what if we're asked to do this? Okay, everybody, what's 3/5 divided by, say, I don't know, 1/5, right? From elementary school. Okay, keep the first number. Fine, 3/5 stays the same. Flip the second fraction and change that division sign into multiplication and then simplify that whole thing. In this case, the answer is 3. 3/1. Okay, quick example about dividing fractions. So when it comes to polynomials and rational expressions, all you have to do is basically flip the second one and everything else is basically the same. Not that exciting, yeah? I notice with the first fraction that that one can be factored out with a Monomial Gcf. Let's do that. Take out an x. Great. And the second one, I'm going to go ahead and change the division to multiplication, and I'm going to do it upside down, okay? 6 minus x, ooh, that looks very familiar, doesn't it? Doesn't that require maybe perhaps a -1 trick in there? That might be it. So I'm going to do that just because I think it's coming. Take out a -1 from that 6 minus x, and I'll be given having a result of -6 plus x. In the denominator. 3x squared minus 18x, I can take out a Monomial Gcf as well. And when I do that, I'll be left with a 3x times x minus 6. Oh, yeah, there it is. Okay. So let's get the domain out of the way, though. Okay. The domain out of the way is all real numbers except x cannot equal to 0, -9, and +6. That's based off of these factors in the denominator before I even reduce anything. Right there, and on the back end there. So there's your 0, there's your -9, and there's your +6, which will make it 0 in the denominator. That's why those are not part of the domain. After you do a few of these, things just kind of go away pretty quickly. Now let's go ahead and cancel things. X minus 6 will cancel with a -6 plus x. That will go away. Oh, the single x right here will cancel with a single x up there. And that leaves me with my simplified solution of, oh, I'm going to move this -1 upstairs, -3 over x plus 9. It really doesn't matter where we put the negative sign, but that is the simplified answer. Okay. Moving on to letter B here. Parenthesize. And looks like I only need a, oh, great. This is actually easier than the first one. Take out a monomial GCF there. On top, take out a 2x. That leaves me with x minus 6 over x plus 5. I'm going to multiply by reciprocating. Keep in mind, I'm reciprocating now. That's my flip. I may have forgot. Yeah, I did forget. I'm flipping those right there. I'm going to flip those right there. Sorry about that. I do these so fast that sometimes I forget to write this all down for you guys. Flip those. That's called reciprocation in the algebra world. And then look, nothing else left to do. Oh my gosh, look at the domain. The domain is based off of here, -5 and 6. So x cannot equal to -5, otherwise it would be a 0 in the denominator, and x cannot equal to 6. And guess what? Things cancel. Let's cancel fast. And there's your simplified version. Yay. Woo. A lot of work today. We're approaching an hour, aren't we? This is turning out to be a big session. All right, we are going to skip example 6 and go to the last problem. Next page. Oh, yeah. Hang in there. Pause. Come back to this later if you need to. Let's go ahead and simplify this. Number 5. By now, you guys are probably experts. X squared minus 36 is the difference of squares. X squared plus 3x minus 18 is just a regular quadratic. X squared minus 36 breaks down to x minus 6, x plus 6. X squared plus 3x minus 18, you can guess and check there. What times what equals -18? When added together, will give me positive 3x. I mean, back in Algebra 1, you'd have gone through all the possibilities, right? 1, 18, 2, 9, 3, 6. And there's one pair, of course, 3 and 6 work. One of them has to be negative, one of them has to be positive, and there it is, okay? So here, those cancel. Forgot about the domain, didn't I? The domain are all values that allow the expression to be simplified, except x cannot equal to, let's take a look here, positive 3 and -6. Right? Those are not part of my domain. They make the denominator 0. And my simplified answer is x minus 6 over x minus 3. All right. Whew. That went a little faster, didn't it? Number 6. Find the product. Again, parenthesize those polynomials. You might be tempted to cancel things. Let's crank through this thing. Y plus 3, nothing happens there. Y plus 2. The numerator, we have a standard quadratic, and the denominator, we have a difference of squares. That difference of squares, of course, is x minus 3x plus 3. Oh, I'm using x's there on accident. It should be y's. Ha ha ha. And in the numerator, oh, that's a perfect square trinomial. I just recognize that. Psst. Y plus 2, y plus 2. Let's look at the domain. All real numbers, y. Oh, weird. They use the letter y. It's confusing. They cannot equal 2. These answers. And they are not part of the domain. And let's see if anything cancels. I love this part. Bye-bye, 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 bye-bye. And there it is. Y plus 2 over y minus 3 is my simplified expression. Woo! Guys, ready for the last one? I'm ready. Ready, here we go. Number 7. Again, feel free to take breaks if you need to. Find and simplify the ratio of the volume. That's crazy. But it's not as crazy as you think. The word ratio is basically division. They want us to divide the two volumes. Now, these are called, technically from geometry, rectangular prisms. Yeah? Rectangular prisms. It's a rectangle base. It's a prism because you're extending the base upward. This is like basically a box of Kleenex, yeah. And the volume is a simple formula. It's just length times width times height. Very simple. I mean, if you look at each of the box, they have a length, a width, and a height for each of those. So we're just basically throwing them into the numerator and the denominator. That's it. There's your length for figure A, width, and your height. Put that in the numerator, and we're going to ratio that with the second figure down there. Not a big deal. Looks like they don't ask us about domain. We'll just have to reduce it. Just a couple x's there and another x right there. That's it. I wish some more would go away. That's the final answer, I guess. 3 times x plus 1 over 2 times x plus 2. That's your ratio. Not that exciting, but it works. This is the ratio right there. We're going to just divide. Well, that's it for me. Thank you very much. We just got it under an hour. Crazy stuff. Anyway, have a good day. See you next time. Thanks a lot. Bye-bye.